In chapter 21, we continue our exploration of the nucleophilic acyl substitution of carboxylic acid derivatives, things that have 3 bonds to an electronegative element. In particular, most of the reactions involve replacing one of the leaving groups with another nucleophile that will replace it. In the previous chapter, all of the examples we saw were strong nucleophiles adding to acid derivatives, in which there was a 2-step mechanism with nucleophiles adding to the carbonyl carbon, followed by elimination of a leaving group to reestablish the polar pi bond. In the current chapter, we look at weaker nucleophiles and also at leaving groups that are less willing to leave. In particular, if we start off with a nucleophile that's a weak nucleophile like water, alcohol, or amines, we can end up making carboxylic acids, esters, or amides. And in doing so, we're going to have our nucleophile, which is a weak nucleophile, adding to our strong electrophile acid chloride. This will also work for anhydrides, creating a charged intermediate, a zwitterion, plus minus, which will kick out its leaving group and then has to undergo a third final deprotonation step to give the neutral product. On the other hand, if we have a leaving group that is not very willing to leave reacting with a nucleophile that is a weaker nucleophile, we need to do a few more acid-base reactions to make the whole thing work. To start with, because the weak nucleophile cannot directly attack the poor electrophile that is an ester, carboxylic acid, or amide, we would first need to protonate the carbonyl to make this a superactive position for reaction. Carbonyl is now activated and our neutral nucleophile is capable of adding to it, creating a tetrahedral intermediate. In solution, any of the sites that are not protonated, such as the Z with its lone pair, can be protonated. Any of the sites that can be protonated can be deprotonated with a base, as long as the whole molecule maintains a net neutral or positive charge. Okay, so one of the other protonation states has the Z protonated, which will now be the leaving group, and the nucleophile is no longer protonated. Because the Z is now a good leaving group, the double bond can be reestablished to make the protonated product, which after another acid-base reaction to remove the extra proton will end up with your nucleophile replacing your Z. Your nucleophile, again, without the H, would be OH, OR, or NR2, and again, that's a way to create esters, acids, and amides. One interesting application of this types of chemistry is the Hell-Volhart-Zielinski reaction. This reaction turns a carboxylic acid with an alpha hydrogen into a halide substituted carboxylic acid. Now we've seen using base and halogens to replace hydrogen in past chapters. However, in the current chapter, that won't work with the carboxylic acid present. Instead, we go through a multi-step process where we have PCl3 and the halide in the first step, followed by water. In the presence of PCl3, carboxylic acids are able to be converted to acid chlorides. This is a very useful reaction for many syntheses because if you have an acid chloride, it is easy to substitute that chlorine with any other nucleophile. This works very similar to the way that PCl3 allows primary and secondary alcohols to undergo SN2 reactions. That is, the oxygen coordinates with the phosphorus to make it positive and a good leaving group, and one of the chlorides comes along, does a nucleophilic addition, tetrahedral intermediate, elimination of our good leaving group with the O phosphorus bond. That will give us our acid chloride. Our acid chloride now is able to undergo our alpha substitution reaction by forming an enol, doing bromination, and then retautomerizing to the ketone, much like we did when we first saw enols brominate back in the SN2 chapter. Finally, this acid chloride will react with water through another nucleophilic acyl substitution reaction, just like the one here. That is, the active acid chloride will react with the weak nucleophile water, create a positively, negatively zwitterionic charged intermediate, the chloride will leave, and after deprotonation, we end up with this OH from water, and we end up with our alpha bromo product. In this chapter, we also get to see what exactly is a mesylate, tosylate, and triflate. We've been using these things in the past as good leaving group. For example, ROMS, ROTS, ROTF. These were good leaving groups for E2 and SN2 reactions. and they're formed from alcohols. Alcohols act as a nucleophile towards this carbonyl equivalent, this sulfonyl chloride. Sulfyl with the double bond, S double bond O's, acts just like a carbonyl. Nucleophile comes in, we create an intermediate with a single bond to oxygen, chlorine leaves. We now have an oxygen-sulfur bond, and after deprotonation we have our mesylate, tosylate, or triflate. The difference between mesylate, tosylate, and triflate is the identity of the R group on the end. This R group can be methyl or methyl sulfonate. It can be a trifluoromethyl or triflate group. Or it can be a para-methylbenzyl, known as a toluene group, like toluene, known as a tosylate. Another important reaction of carboxylic acid derivatives and of nucleophilic acyl substitution with weaker nucleophiles is the Claisen condensation. The Claisen condensation is the equivalent of an aldol reaction, except using esters. So, for example, an ester will condense with itself to make a product that has two equivalents of the ester in it. Here would be carbon 1, carbon 2, carbon 1, carbon 2. There's a new alpha-beta bond, and there's a second ester, carbon 1, carbon 2, OR, alpha carbonyl OR. This happens because if you put a base, and we usually choose the base OR minus that is the same OR that is on the ester itself, if you choose a base that is strong enough, you can remove a hydrogen at the alpha position of an ester to make an ester enolate. This creates an equilibrium of ester enolate and ester, and the enolate of the ester can actually react with the ester itself in a nucleophilic substitution. Once you've eliminated the second OR group, you end up with your beta keto ester product. Here's the ester, alpha, beta is the keto. And Claisen condensations are the topic of Chem Activity 26C. The product of the Claisen condensation, the beta keto ester, shown down here, is a good substrate that can be used to create a nucleophile for SN2 reaction. That's the basis of the acetoacetic ester synthesis, also in Chem Activity 26C and D. So what happens is your base, in this case we're using RO minus again, pulls off an alpha hydrogen. This alpha hydrogen is actually alpha to 2 carbonyls and so is doubly acidic. It then does an SN2 reaction with an alkyl halide, and for this purposes the alkyl halide must be primary or methyl. The product of this reaction forms a new carbon-carbon bond between this carbon, which was the enolate, doing an SN2 with this R' group. There's your new bond. You can actually repeat this reaction and put a second R' group on. You can hydrolyze the ester that's attached by adding acid and heat, and that will allow us to do a nucleophilic acyl substitution reaction to convert an ester to an acid, and that creates a product with our new carbon-carbon bond and a carboxylic acid. Notice I've kind of drawn the carboxylic acid turned around the sigma bond right here. When this reaction is heated, it undergoes a spontaneous decarboxylation, electrocyclic reaction in which the electrons move as shown in the picture, eliminates CO2 to form an enol. As we know, enols do not hang out but are in equilibrium with the corresponding. So our final result of the acetoacetic ester synthesis is that this whole part over here, the carbon OR, has been turned into a carbon OH and then eliminated as carbon dioxide. The part over here, the methyl ketone part of the molecule, is retained in the product, and there is a new R group that has been added through our SN2 reaction. Our final topic for this chapter is protecting groups, and particularly protecting groups for carboxylic acids and amines that are created and removed using reactions from nucleophilic acyl substitution along with proton transfer, the reactions from this chapter. One of the things we looked at protecting is carboxylic acids. Carboxylic acids are quite reactive as acids because of their acidic hydrogen and often need to be protected. The most common way to do so is to make them into esters. And we can make them into esters directly by using an alcohol such as methanol and an acid, doing a nucleophilic acyl substitution to create the ester. Or we can use diazomethane, which converts carboxylic acids through SN2. into methyl esters. Finally, another common alcohol to use is benzyl alcohol. And this is a good one to make a benzyl ester because these benzyl esters are easily removed by our removing conditions. In all three cases, the ester can be turned back into the carboxylic acid as is needed for protecting group. You need to be able to put the group on, ester, and off again. And all three of these esters are readily hydrolyzed with acid and water and heat back to the original carboxylic acids. Finally, amines are quite nucleophilic and basic, but can be made much less reactive by turning them into unreactive amides. This is done by reacting them with acid chlorides, which makes the corresponding amide, which can be hydrolyzed readily to regenerate the carboxylic acid that we throw away and give back our amine.